The Southern Gas Corridor included the two main pipelines, TANAP, which is crossing Turkey, and then followed by the TAP, which is crossing Greece, the whole pipeline bringing gas from Azerbaijan to Europe. So for the first big part, the TANAP in Turkey, we supplied more than 300,000 tons of steel. Grade was X70. In high thicknesses, two main thicknesses, it was more than 16 mm and 19.63 mm. Specification was a mix between high strength, X70, high thicknesses, that I just mentioned, but also very strict and severe toughness requirement on drop wear tear tests at -10 degrees on coil. So the mix of these three main parts was really difficult to achieve. And that's why our concept of low carbon and high niobium, coupled with a specific thermomechanical rolling, was really successful and allowed us to achieve these specifications. For the Greek one, the TAP, we delivered 75,000 tons, again in X70, so the same grade, same concept from ArcelorMittal Bremen. The thickness was 17.9 mm. And but with a more severe toughness requirement of drop wear tear test at -20 degrees on coil.
The most difficult property to be achieved on pipeline steel in heavy gauge is toughness at low temperatures. This property is tested by Battelle drop weight tear test, and this test mainly depends on fineness of the microstructure and homogeneity of microstructure. This property can be very well mastered by careful control of the thermomechanically controlled process, and traditionally during this process it is aimed towards high strain accumulation, which follows afterwards with accelerated cooling. Therefore, we have to carefully choose the processing parameters in order to master these properties. And their main role of niobium comes to a light because it is known that niobium delays the softening kinetics of the steel, and niobium also influences the grain mobility of austenite. And this is done by means of a solid drag effect and by strain-induced precipitation of niobium carbides. So in concept with high niobium and low carbon, it is possible to do the process in high temperature window, and exactly this represents the relaxation of temperature constraint in our finishing train, and also allows us to obtain the desirable microstructure, that is fine-grained microstructure. ArcelorMittal Bremen has a very powerful roughing and finishing mill, capable to thermomechanically roll large cross sections. During this process, the rolling is done below recrystallization temperature, where we have accumulation of deformation, and this imposes the higher rolling forces in the finishing mill especially. By adding niobium, we increase recrystallization temperature and have relaxation of the temperature constraint in our finishing mill. We don't have high mill loads, and we get desired properties much easier.